Swayamprabha. Digital India. Educated India.
So, welcome to the 26th lecture of Cryogenic Engineering, and here we will be talking about a new module now, which is Cryocoolers, which is I said new module, and this will consist of various subtopics and which will be covered over next 6 to 7 lectures. We will talk under Cryocoolers, cryocooler fundamentals, different types of cryocoolers and their applications. Then we will go in details of Stirling type cryocoolers, pulse tube cryocoolers, Gifford-McMahon cryocoolers. When I said in depth means we will not go to the design, we will go in details about Stirling cryocooler, and I can give you glimpses of how pulse tube cryocooler, GM cryocooler work and things like that. Then we will also have a glimpse of various important parameters, very important sub parts of the cryocooler, which is a regenerator, heat exchangers and compressor. At the same time, a lot of work has been done at IIT Bombay, and I would like to show the cryocoolers being developed at IIT Bombay, so that you can get a direct feel of the hardware which has been developed at IIT Bombay. Also, you can see possibly a working cryocooler which can give you an impression about what is the cool down time, what is the temperature it reaches and things like that. This topic we will try to cover in around 6 to 7 lectures depending on how we go through these topics. Again, we have got tutorials and assignments are included at the end of each lecture as what we have been doing till now. So, now coming to cryocooler, and the first lecture we will talk about what is a cryocooler, alright, how does it work, what are different types and things like that. So, what is a cryocooler, and importantly why do we need a cryocooler? Cryocooler is basically a device which generates low temperature. So, what is the need when you got a liquid nitrogen, liquid helium, all these cryogens which give you low temperature, then why do we require a cryocooler? Then we talk about the classification and basics of different cryocoolers. And then lastly, I will just cover in 2 or 3 slides what are different applications of this cryocooler. There were plenty of applications, but I cannot cover all of them in detail. So, I will give you a field wise usage of these cryocoolers. Alright. Now, let us see what is a cryocooler. So, cryocooler is a mechanical device which generates low temperature due to compression and expansion of gas, a simple thing. It is like any other domestic refrigerator. A cryocooler actually is nothing but a refrigerator which gives you cryogenic temperature, which generates temperature in cryogenic range, and actually some people will call it cryogenic refrigerator also. So, a cryo refrigerator, cryogenic refrigerator or a cryocooler, there are different names they will attribute to this device, but essentially what it does, it works like a domestic refrigerator. There is a compressor, there is a heat exchanger and there is an expansion device. So, you can see here in this particular schematic what you have is a compressor, then heat exchanger, then there is expansion device, and lastly we have got evaporator to do the heat exchange with the object to be cooled. So, this operates in a closed cycle manner. So, you can see the arrows in both the directions. So, gas gets compressed, comes to heat exchanger, exchanges heat, gas gets expanded, produces cold, gives the cold to the object to be cooled, and the gas goes back and the cycle continues. So, important thing about cryocooler is it operates in a closed cycle manner, which means the mass of the working gas is constant. So, once you charge the cryocooler, like again in a domestic refrigerator which also works in a closed cycle manner, if I charging some amount of gas, this gas will be compressed and expanded, which generates low temperature. So, once you charge the cryocooler with a given amount of gas, it will work in a closed cycle manner and generate a cryogenic temperature, and whatever object you want to cool, if you want to cool the gas, if you want to liquefy the gas, that is also possible using a cryocooler. So, cryocooler can also work as a liquefier provided it generates that much amount of cold or cooling effect or refrigeration effect. So, as I said, it operates in a closed cycle manner, which means the mass of the working gas is constant. A cryocooler consists of a compressor, a heat exchanger and an expander as shown in the schematic. So, when I say expander, actually it houses both expansion device as well as evaporator. It combines, and this can be called as an expansion unit. The cold generated in the expander, so a lot of cold is generated in the expander which houses both expansion device as well as evaporator. is exchange between the cold end and the object to be cooled. So, whatever object is to be cooled, this object will be over here. So, it's actually evaporator is nothing but a kind of heat exchanger which transfers this cold to the object to be cooled. All right. So, this is a closed cycle manner in which the cold will be generated and it will exchange this cold through evaporator to the object to be cooled. So, cryocoolers are capable of producing temperature as low as 77 Kelvin or below 4.2 Kelvin, not only 4.2 Kelvin, but below 4.2 Kelvin, and they will be used to replace the cryogen. So, at many places you can't go for liquid nitrogen or liquid helium or liquid hydrogen for that matter, because of the availability and because this cryogens cannot reach there in time. So, what do? We use a cryocooler. It generates whatever temperature is of your interest. Any temperature from in a cryogenic zone below 120 Kelvin, a cryocooler can be designed for that particular application to generate that much of cold, and it can therefore replace whatever was earlier done using a liquid helium or a liquid nitrogen or a liquid hydrogen. So, that is a very important usage of cryocooler. Like a domestic refrigerator, it can generate. Domestic refrigerator is meant for particular purpose. However, cryocoolers can be designed for a particular purpose. It can be customized for a particular purpose to generate a given temperature and also to generate a given cooling effect. It's very important. So, why do we require a cryocooler? And I will just go through a title of this particular paper. This article shown here is extract from a Asian Age on 23rd August 2010. What does it say? It says that Earth's helium reserves to run out by 2030. Earth reserves are obtained mostly in USA through the rocks or through the different springs, hot springs over there, and this helium reserve is getting depleted over a period of time. The helium gas is very, very costly. So, if I want to use liquid helium, the cost of liquid helium is going up and up. So, if I want to have a 4.2 Kelvin, I have to really pay a lot of amount. Instead, can I use now a cryocooler which generate the same temperature? And because why this application is felt very, very importantly right now is because of this reason that helium reserves are running out by 2030. So, according to Professor Robert, who is from Cornell University, helium reserves would be running out by 2030, and therefore, the closed cycle cryocoolers will replace liquid helium. What was previously done with liquid helium, because the cost of liquid helium is going to go up and up. All right, it is very difficult to extract helium from air. The cost of extraction of helium gas from air is 10,000 times more, and therefore, whatever helium reserves are available right now in the rocks, for example, because this is getting depleted, the cost of helium is going to go up, and that can be completely replaced, or its function can be completely replaced by using a closed cycle cryocooler or a cryocooler which generate the same temperature, and this is the need of the time. This is a very important function, and therefore, most of the cryogenic applications would now use cryocoolers instead of liquid helium. All right. So, it's a very important fact. A cryocooler can actually do away with the usages of liquid nitrogen and liquid helium. So, why a cryocooler? Again, taking the same topic ahead, why a cryocooler? Importantly, I just pointed out, if I use a cryocooler, I may or may not require a cryogen now. This is very important. I will not require liquid helium now, which is the most costliest cryogen right now. So, a cryocooler can function to produce a temperature which was otherwise given by a liquid helium. So, in this case, I will not require any cryogen. Cryocoolers offer reliable and maintenance-free operations. Because of the usage over a period of time, cryocoolers have become very, very reliable and maintenance-free now, and therefore, they are acceptable in most reliable functions required. For example, in medicine, for example, in healthcare unit where reliability plays a very important role, and cryocoolers have been accepted over there. The cost of cryogen is increasing while the cost of cryocool is coming down. This is a very important parameter. As I said, because of the helium reserves are depleting, the cost of cryogen is increasing with time. Okay, there are various losses in transferring of cryogen. There is a safety requirement again while transferring cryogen. Plus, in addition, that these gases are becoming rare. For example, helium, neon, etc. While the cost of cryocooler is coming down because more and more cryocoolers are made, and therefore the production costs are coming down, and a lot of new technologies are coming into picture, and therefore the cost of cryocooler is coming down, which is again a good reason to replace cryogens. What was previously done by cryogens, now cryocoolers can do the same important thing. There is a scope for new technology which would advance development toward invisible cryogenics. Now, this is a very important statement. The cryocooler technology has always been a dynamic technology, and every time, if if you go for any conference, every time you find that something new is happening, something new has come in this field, and therefore, this technology is always becoming new, better and better, efficient and efficient, and therefore, this is a very, very important thing that the technology is becoming better and better with time. And also, for example, the physics people or the healthcare unit, they don't want to know about cryogenics. They want low temperature, no matter how you get it, but they don't want to see the cryogenics associated with that thing, because for example, in hospitals, they want low temperature to perform surgery, for example, or run a MRI machine. They are not bothered about how you generate low temperature. So, a new phrase is, we would like to go towards invisible cryogenics. That means, if I am a user from physics department or from, let's say, from medicine side, what I want is, I want low temperature and I don't want to worry about how do I get low temperature. That means, cryogenics for me should be invisible, and this is where everybody would like to go. The cryogenics should become invisible, and a reliable and maintenance free cryocooler can do the same thing basically. So, this is what we are aiming for. Now, coming to cryocooler classification. If I see cryocooler classification, the cryocoolers can be classified based on how you get cryogenic refrigeration. So, this is the most important thing. So, I can get cryogenic refrigeration in two ways. One is by open cycle, the other one is by closed cycle. Please understand this slide very importantly now. So, if I want something to be delivered at 4 Kelvin, 10 Kelvin, 25 Kelvin, 30 Kelvin or 80 Kelvin or whatever, we can get this cryogenic refrigeration by two ways. One is by having open cycle, one is by having a closed cycle. When I say open cycle, that means the gas or the cryogen which is used is open to atmosphere, the gas is delivered to atmosphere. Closed cycle, as I said, the cryocoolers where the gas or whatever cryogen we use works in a closed cycle manner, it is not left to the atmosphere again. Okay, let us come to the open cycle, and under open cycle now we can use stored gas or stored cryogens. So, I can have a stored gas, and under stored gas I can have a Joule-Thomson cryocooler. A JT is nothing but Joule-Thomson cryocooler. I can expand this stored gas from high pressure and expand the gas from high pressure to low pressure, during which I get a cooling effect, and this cooling effect is delivered to whatever to be cooled. That means, I get cryogenic refrigeration, and this gas is let go to the atmosphere. For example, I can use nitrogen here. Nitrogen at a high pressure going through a small constriction or a capillary tube expands, it gives the cold and the gas is left to atmosphere, alright, and this is what we call as open cycle. The other part is, instead of stored gas, I can go to stored cryogen. I can use liquid nitrogen, liquid helium for example. I can use this to cool whatever object I want to cool, and this gas, after delivering the cooling effect, it can again let go to the atmosphere, alright. So, that is why we call it open cycle. We do not collect it back and compress it back and things like that. So, here I can use solid cryogen, liquid cryogen, supercritical cryogen. So, stored cryogen I can use in any form. If I go on cooling liquid nitrogen further, I will get solid nitrogen here, alright, which possibly will happen below 63 Kelvin. And this solid nitrogen also could be used to deliver cooling effect. I can use liquid nitrogen, I can use compressed supercritical nitrogen gas to deliver this cold, alright. So, these are different ways of getting open cycle, to get cryogenic refrigeration by using an open cycle. Now, let us come to closed cycle. Under closed cycle, you have got two possibilities. We have got a device which works in a dynamic way, we have got a device which works in a static way. When I say dynamic way and static way, I am talking about a moving component. When I say dynamic, that means something is moving, either the compressor piston or expander or whatever it is. There is one part which is always in motion, while static, nothing is moving. So, ideally I will prefer to have a static, because the moment there are no moving parts, there is a maximum reliability, there is no wear and tear, alright. So, static is the most sought for, right, but it has got its own problem. So, dynamic delivers cold very fast and more efficient also, but then you have to pay for it, because there will always be some wear and tear. So, we got a dynamic possibility, dynamic closed cycle or a static closed cycle device, and under these devices now, under dynamic for example, we have got different classification based on the heat exchanger it uses. As I said, every refrigerator or every cryocooler will have a heat exchanger, and this heat exchanger will could be of a recuperative type or a regenerative type. We will talk about this in detail. So, depending on the kind of heat exchanger they use, they can be further classified as a regenerative cryocoolers or a recuperative cryocoolers. Okay. Under regenerative now, I can have valves between the compressor and expander, I can have valveless unit between the compressor and expander. So, this also makes a difference because whenever valves come, efficiencies are a problem, all right. And under valves now, or under valveless system, what you have is different types of cryocoolers, and under valves what we have is a GM, Gifford-McMahon cryocooler, and we have got a Gifford-McMahon type pulse tube cryocooler here. While a valveless unit is always a Stirling cooler or a Stirling type pulse tube cooler, and we will go through details of these because a cryocooler is a part which is dealing with this quadrant here, all right. So, we will go through this more in the coming lectures. Under recuperative, what normally you have is a Joule-Thomson or a Claudet type of cryocoolers. We have dealt with Claude cycle and Jetty cryocoolers earlier. So, here pointing out GM is nothing but Gifford-McMahon, Jetty is nothing but Joule-Thomson cryocooler. So, this is what we will be dealing with in the next 4 or 5 lectures. While under static, we have got various possibilities. As I said, in static cryocoolers, nothing is moving, and therefore, we can have a sorption mechanism where gas is actually adsorbed on the sorption material, and therefore, sorption cryocoolers, we can have radiative cryocooling, which is normally used in space. We got a magnetic refrigeration, we got a cooling due to lasers also. Most of you possibly may have heard about that, about these kinds of cooling devices based on the principles I am writing here. So, you got no part in this case is moving, and therefore, you got a maximum reliability. Only thing is what you require is very high cost sometimes, or the system could be very less efficient in this case. So, as far as these lectures or this module is concerned, we are going to talk about this third quadrant. If I call this as third quadrant, whatever has been enclosed here, this is what we are going to talk about in this module of cryocoolers. Now, depending on the end use application, the basic requirement as given below have to be satisfied by the cryocoolers. So, what are these requirement to be satisfied by the cryocoolers? It has to have less weight and small volume depending on end use. For example, it can be used in space application where the weight and the volume also are very important. Fast cool down time and vibrationless operation. This is also a very important characteristic. How much time it takes when started, how much time it takes to reach down to the lowest temperature, and also what is its vibration level, noise level. These are also very important parameters depending on the kind of applications you have in mind. Now, different parameters associated with the maintenance and life is basically MTBM. The mean time between maintenance should be as minimum, mean time between failure should be as minimum, as well as mean time to failure. These are typically MTBM, MTBF and MTTF are the terms which are talked about when we are talking about its life, and this should be definitely, this should be very high. Continuing further, the basic requirements of a cryocooler are, if I want to technically see what are cryocooler requirement, it should have minimal effect of orientation. Sometimes the cryocooler or some of the cryocoolers do not work when their orientation is not vertical. If they are inclined, for example, pulse tube cryocooler which we will see, it has got its orientation effect. Acoustic noise, electromagnetic interference, because some parts are moving all the time, and therefore, the devices around this cryocooler can also show some problems because of the interference. So, you have to worry about in what environment these cryocoolers are going to work, and accordingly one has to choose or one has to shield these cryocoolers. The cryocoolers of course should have high reliability and shelf life. Cost effective as compared to existing system. Now, sometimes these cryocoolers can be very costly depending on what temperature you want to use, and different customizations can be made, and therefore, the cost effectiveness of this cryocooler has to be justified, and this is the normal parameters which one has to consider when one chooses or buys a cryocooler. Now, what are technical parameters? When I buy a cryocooler or when I decide to design a particular cryocoolers, what are the technical parameters that govern the choice of a cryocooler? So, if I want to design a cryocooler or if I want to buy a cryocooler, what are various parameters I will look for? All right. So, important thing is cooling effect, and the cooling effect is how many milliwatts of cooling effect at a particular temperature, or how many watts of cooling effect at a particular temperature. For example, I require 50 milliwatts at 80 Kelvin. Do I want it? If I want to use this thing, this is my design specifications. So, one has to really know, and mind you that for this we are paying. If I say instead of 50 milliwatt, I want 500 milliwatt, the cost of the cryocooler will be very high. So, therefore, one should be clear for what exact end use application a cryocooler has to be designed or a cryocooler has to be bought. There is no point in buying a very high capacity cryocooler if our requirements are very low, because one will pay for this cooling effect, because the size of compressor, size of expander, size of entire cryocooler will change as soon as one demands higher cooling effect at any temperature. The next parameter which is very important is what is the compressor power requirement. It could be in watts, it could be in kilowatts. So, to obtain this cooling effect, compressor power also is to be decided. In fact, this upon this is nothing but the COP of a cryocooler, isn't it? So, compressor power requirement is a very critical parameter, because the power requirement sometimes could be available or may not be available depending on in what environment you are working. Do you have a 3-phase requirement, for example? All right. Do you have a single phase requirement? This is also a very important parameter when one decides to buy a cryocooler. Now, many times the compressor needs to be cooled. There is the aftercooler. Do we require a cooling water? Do we require chilled water requirement? So, when I buy a bigger compressor, I may go for a cooling water requirement, and therefore, I will require a chiller, and that is also an additional cost. So, I should know, do I require, is it a air cooled compressor or a water cooled compressor? There are different parameters associated with this, and one should be aware of all these technical parameters. Again, one has to worry about service requirement of a compressor, because this compressor could be oil filled compressor. The moment they are oil filled, the oil needs to be changed over a period of time, or even the adsorbers needs to be cleaned or replaced over a period of time, and this talks about service requirement. Maybe after 10,000 hours of working or 15,000 hours of working, this is required to be done, and therefore, one has to know what are the service requirement, because when the compressor is being serviced, your cryocooler will be down, and if your application, for example, is in health services, the downtime is very costly. So, one should be aware of such parameters, and of course, the vibration level and the cost which I have talked about, all this will constitute kind of technical parameters, or it will govern the choice of a cryocooler to be used for a particular application in mind. Now, let us come to the classification of cryocoolers, and as I said earlier, the cryocoolers are classified based on the kind of heat exchanger it usage. So, every cryocooler will have some kind of heat exchanger, and every heat exchanger, the heat exchanger could be of two types, a regenerative type and a recuperative type, and I will talk about this in the next slides. So, if you have got a regenerative type of heat exchanger, then we can have different cryocoolers, like we can have Stirling cryocooler, Gifford-McMahon cryocoolers and pulse tube cryocoolers. They all come under category of, they all use regenerative heat exchanger to cool the gas, where heat exchange happens, while a recuperative heat exchanger under this category, what falls is Joule-Thomson cryocooler and Claude cycle and Brayton cryocoolers also. I will talk about this. So, this is a very important cryocooler case which uses regenerative cryocoolers, regenerative heat exchanger based cryocoolers, and sometimes they are called as regenerative type cryocoolers also, while this is a recuperative type of cryocoolers. So, based on the heat exchanger the cryocoolers use, we have got a regenerative heat exchanger, a recuperative heat exchanger, and different types of cryocoolers come under that. So, a heat exchanger is a device in which the warm fluid gets cooled due to heat exchange with cold fluid, as you know this. In most of the cases, the process of heat exchange occurs at a constant pressure. It can either be a regenerative heat exchanger or a recuperative heat exchanger depending on the kind of heat exchange between the fluids. So, you know the basics of heat exchanger, where warm and cold fluid exchange heat. Now, in a recuperative heat exchanger, the flow direction of two fluid is constant and is simultaneous. So, you can see that this is a recuperative type of heat exchanger where the hot fluid goes and the cold fluid comes down, and this direction of hot fluid is always constant. It will not change over a period of time, and both these fluids, the hot fluid and the cold fluid, are moving simultaneously. Both of them are present at the same time. The two fluids are separated by a solid boundary across which the warm and cold fluids exchange heat. Now, this is also very important that the cold and hot fluid are actually segregated. They are away from each other, and the heat exchange happens between some copper tube, for example. So, we can have a tube in which one tube is housing a hot fluid, the other tube is housing a cold fluid, and through the thickness of this tube or the surface area of this tube, the heat exchange is happening. So, actually they are basically separate, they are housed in a separate tubes sometimes, or separate channels or separate sections. The direction of the fluid flow may either be counter flow, cross flow, or parallel flow, as explained in earlier lectures. If you have seen my liquefaction lectures, we have talked about the recuperative heat exchanger there, and these directions can be parallel to each other, cross flow, counter flow kind of recuperative heat exchangers. Alright. So, these are the recuperative heat exchanger which are normally used in Joule-Thomson cryocooler. Now, let us see regenerative heat exchanger, and in the regenerative heat exchanger, a matrix is used as an intermediate heat exchange medium between the warm and the cold fluid. So, you can see here, in addition to the warm fluid and the cold fluid, what you have is a matrix in between. So, what happens here? The flow is periodic. That means, I will have a hot fluid going through first for some time, and this hot fluid will give the heat to the matrix, and this matrix will take the heat and store the heat. After some time, when the hot fluid has gone, the cold fluid will come, which could be the same fluid at lower temperature or a different fluid also. This cold fluid will come, and this cold fluid will pass through the regenerator, and it will take heat from this matrix, and it will get warmed up during this period. So, we got a hot blow followed by a cold blow, and the hot and the cold fluids are actually not moving at the same time. So, what does it mean? It means that they are oscillating flows. The flow is in this direction for some time, and flow then in this direction will stop, it will come to 0, and then the cold fluid will start after some time. Alright. So, it is very important to understand that the heat exchange is happening through a matrix, and therefore, we say that the flow is periodic in nature. So, in this case, the flow is periodic in nature, alternating between the warm and the cold fluids across the matrix. It is important to note that it is an example of indirect heat transfer. That means, there is no direct heat exchange between the warm fluid and the cold fluid. The warm fluid gives the heat to the matrix, and then the matrix passes this heat to the cold fluid. So, there is an indirect heat transfer between the hot to the cold fluid through the matrix. This is the way the regenerative heat exchangers work. Now, in recuperative case, if I want to see now recuperative cryocoolers, you got a compressor, a heat exchangers, and Joule-Thomson expansion. So, this is a Joule-Thomson cryocooler which uses a recuperative heat exchanger. The first recuperative cryocooler shown here is a Joule-Thomson cryocooler, which we have seen earlier in a Linde-Hampson cryocoolers also, the cycle also. The gas is compressed in the reciprocating compressor and is expanded isenthalpically based on its inversion temperature. If you remember that Joule-Thomson cooler will produce low temperature only when the gas temperature is below its inversion temperature, and you get a cooling at this point. So, simple Joule-Thomson cryocooler will have a compressor, or you get a high pressure side and a low pressure side with valves over here. You can see the high pressure gas will come, it will get expanded by this expansion device, produce the cold, and the low pressure gas will go back through a recuperative heat exchanger. It will pre-cool this incoming high pressure gas, and it will go back and cycle will continue. This is the way a Joule-Thomson cryocooler work. The hot and the cold fluid exchange heat in a recuperative heat exchanger in this case. Now, you can have the second cycle, which is Brayton cycle. Instead of having this valve, we can have an expander, which is a moving expander, and it has got inlet valve and exhaust valve. And depending on this expansion, this will produce work output over here. This will not produce work output here, but this will produce work output, and therefore, what we call is a Brayton cycle. And the third cycle will be a combination of this. So, this cycle is a Brayton cryocooler cycle similar to Joule-Thomson cryocooler, except that the expansion device produces work. And the third is a combination of these two. So, we have got a Brayton work output also, at the same time we got a JT also, and we have got a 3 recuperative heat exchanger, and this is what we have explained earlier, Claude cycle, if you recollect. Alright, so we have got 3 devices, 3 different cryocoolers which work on recuperative cryocoolers. So, the next type of cryocoolers now we have is a regenerative cryocooler. As I said, the regenerative cryocooler we use regenerative heat exchangers, and they are of various types. So, here we will deal with first what we call as Stirling type cryocoolers or Stirling cryocoolers here. So, here you can see that the schematic is shown, we got a compressor here, and the compressed gas will come through the regenerator. This is the regenerative heat exchanger. At the same time, what we have got is something called as displacer, which is also moving. The compressed gas will come over here, the heat of compression will be removed in this aftercooler here. The gas will come to the top of displacer over here, and during the motion of this displacer, this gas will be pushed, and this will come through regenerator, and the gas will come to the expansion space over here. Alright, and as soon as the pistons go back, the gas will get expanded at this point. When the displacer comes down, this gas will go back, and the cooling effect will be delivered in the evaporator at this time. We will go through the details of working of these Stirling coolers, but just to tell you that there are 2 moving components here, one is the compressor piston and expander or a displacer at this point. This displacer is just displacing the gas. When it comes to the expansion chamber over here or expander over here, this expansion volume, it will just force the gas to go out. Piston compresses the gas, while displacer just displaces the gas, it is not compressing. Alright. So, it will just displace this gas from this, it will come through regenerator, come through the expansion volume or expansion chamber. The gas will get expanded depending on the motion of the piston at this point, and then the displacer will come down and it will push this cold gas out, delivering the cold effect at this point here. The evaporator is housed over here, and this is the way the Stirling cooler works. So, it consists of a compressor, regenerative heat exchanger and a displacer. And the compressor piston and the displacer maintains a fixed phase angle between their motion. So, this red line shows the relationship between the compressor piston and the displacer. This is a very important design aspect. If they are in phase, they will not produce any cooling effect at this point, and therefore, a very important or very fixed phase angle, a correctly maintained fixed phase angle between the motion of the piston and the displacer will be maintained over here, and that is a part of your design parameters which will produce cooling at this point. This phase difference is vital to have a efficient operation. Now, the next cryocooler what we call is a Gifford-McMahon cryocooler, and what you can see here, there is only one line. High pressure, low pressure was traveling from this, while here we got a high pressure line and a low pressure line, separate line, because the compressor kind of compressor used here will have two valves, inbuilt valves over here, which are actually direction dependent valves. So, high pressure gas comes over here, and we have in addition one more valve in between the compressor and the expander. If we call this as expander and this is compressor, we have got some valve here which will allow the high pressure gas to come out for some time, and then high pressure gas will come over here and the displacer is housed here, and suddenly after some time the high pressure gas will stop, because this valve will stop the high pressure gas to come out, and the low pressure valve will open and the gas here will get expanded, producing low temperature, and again the displacer will move down and the gas will be displaced back and it will go to the low pressure and the cycle will continue. So, high pressure gas will come for some time and the low pressure gas will go after some time. So, whatever is the compressor used here, we have got a relationship between the rotary valve or a valve which is used here, some valve kind of a mechanism and a displacer motion. This is very important. So, this schematics Gifford-McMahon cryocooler, the required phase difference again as which was done over here between the compressor piston and the displacer. Now, here it will not be compressor piston and a displacer, but between the valve mechanism which is used over here and the displacer. The displacer will move according to the valve mechanism. When does high pressure gas come in, when does low pressure gas go out. So, required phase difference is maintained by relative motion between the valve mechanism and the displacer motion in case of a Gifford-McMahon cryocooler. The Stirling cryocooler works at high frequency, because you can see here the frequency of the piston will be same as that of the mains, basically maybe 50 hertz, maybe 120 hertz, whatever, and the displacer has to move with the same frequency as that of the piston. Therefore, this is called as a high frequency machine. The Stirling cooler therefore work at high frequency, while the Gifford-McMahon cooler, they do not work at high frequency, it will move at a frequency of this valve. At what frequency the valve opens, high pressure valve and the low pressure valve mechanism works. So, this is normally works between 1 to 5 hertz. So, they are actually called as low frequency machines. Okay? They got different advantages and disadvantages also. So, Stirling cryocooler works at high frequency, while GM cryocooler works at low frequency. In addition to this Stirling and GM, what we have is also pulse tube cryocooler. So, what you can see in pulse tube cryocooler is there is no displacer in the expander here. There is no mechanical displacer over here, and therefore, we do not require a drive for this also. In earlier two cases, because the displacer is moving, we will require a drive mechanism for this displacer motion also. So, pulse tube cryocooler works without having any mechanical displacer. Instead, gas works as a displacer. There is only a tube filled with gas, alright, and all of them have got a regenerator over here. There is no need for a mechanical drive in this case, because there is no mechanical displacer, and therefore, one complete moving unit is got rid of. We have just got rid of one moving part basically, which means this is a more reliable system. There is no wear and tear. There is no need of a mechanical drive for this. So, naturally, the vibration in this case are much less as compared to what they are for Stirling and GM coolers, right, because there is a displacer and there is no displacer in this case. As a result, the magnitude of vibration in pulse tube cryocooler is less as compared to Stirling and Gifford-McMahon cryocoolers. Simple thing. We will go through the details of all these cryocooler in the coming lectures, but I just wanted to highlight the differences or different regenerative cryocoolers. Now, these pulse tube cryocoolers can be with valve and without valve, which means they can be of Stirling type pulse tube cooler, which is without valve, and also they could be of GM type pulse tube cooler, which means there is a valve elements between the compressor and expander. So, this is called as Stirling type pulse tube cooler, this is called as GM type pulse tube cooler. As I said, this is a high frequency machine, this could be a low frequency machine. So, the pulse tube cooler can be of Stirling type or a GM type as shown in this figure. The phase difference is achieved using a inertance tube. What you can see is all these things, when you got a gas moving over here, one has to have some relationship between the gas and the piston motion in order that the cooling effect gets produced. And therefore, there are different kind of phase shift mechanisms which could be inertance tube, orifice, double inlet valves. You may have heard of these things, and we will study this phase shift mechanism in detail in the further lectures. But what you have to see here, because there is no mechanical driven displacer, you get a gas which is moving up, and in order that a particular phase difference gets maintained between this gas motion in relation to the piston motion, we have got a phase shift mechanism which is actually introduced by the inertance tube, orifice, or a double inlet valve, and also you can see a reservoir on the top. These are nothing but other devices which actually introduces this phase difference or nullifies this phase difference. We can see that in the later part. So, if I see all the 4 cryocoolers, you can see a Stirling cryocooler, a GM cryocooler, the difference between, you can identify the difference because of this wall mechanism in between, or having HP and LP line over here. Stirling type pulse tube cooler and a GM type pulse tube cooler. The pulse tube cooler can be highlighted with the fact that there is no displacer shown over here, alright. And the GM can be identified by the fact that there is a wall over here. In this case, wall over here. These are very important things, and all these 4 cryocoolers are very important to understand how do they work. So, with this background, we can see now what is the comparison of efficiencies of a Stirling cryocooler and a GM cryocooler. So, you can see a Stirling cryocooler has got AC power supply which is out from our mains, and what you get here also is oscillating pressures. So, essentially there is no conversion from AC to AC, but there is a conversion from AC to OC. So, what goes in is the oscillating motions over here, which is 20 to 140 hertz, and at the same frequency the pressure will come out oscillating at the same pressure which is fed to the expander. So, there is no conversion from AC to DC or DC to AC. Whatever oscillating motion is here of the piston, the same oscillating motion of the pressure will go to the expander, and this AC to AC, this conversion, all right, could be about 85%. All right, this AC to AC basically is a power transmission from AC, and what you get ultimately is a PV, pressure volume diagram. So, this conversion could be 85% over here, and therefore, Stirling coolers are supposed to be very efficient over here. On the other hand, if you go to GM cryocooler, your supply is main supply again, and therefore, this is oscillating, but here you got a valves in between. And therefore, what you get from here is AC to DC conversion. We get a HP line, high pressure line, and low pressure line defined over here. So, actually we can call this a conversion from AC to DC because of the valves, and assuming that the valve efficiencies are 50% normally, we got a power loss of 50% over here. And again, what is fed to the cryocooler is AC form, because what we want is the pressure fluctuations at this point. So, again this DC is converted to AC, that means oscillating pressures which are fed to the expander due to the existence of this wall mechanism, which is a specific characteristic of a GM cryocooler. So, if I give 100 watts at this point, efficiency of this wall assumed to be 50%, what I get is only 50 watts at this point, and again 50% efficiency at this point. So, what I get ultimately is only 25, all right, and therefore, overall efficiency of a GM cooler is much less as compared to what it is as Stirling cryocoolers. And why it is less? Because of the presence of the valves. This presence of the valves actually brings about inefficiency in a system, and what is delivered as 100 watts input and what is delivered at the outlet is only 25 watts. So, GM cooler is a very inefficient in cycle. So, one has to feed lot of wattages over here in order to get cooling effect at this point. All right. So, because of the presence of valves, it is very important to understand that the efficiency of a GM cooler is much less as compared to what it is for Stirling coolers. Now, let us go through each cryocooler and just see advantages and disadvantages of various cryocooler. So, a JT cryocooler is used for cooling infrared sensors on missiles, surveillance cameras. It can be used for cooling semiconductor electronics, and also recently it is being used for cryosurgery, because the high pressure gas just goes in, it gets expanded, produces cooling, and it can just go out to the atmosphere, or it can be recompressed also. So, there are various usages JT cryocoolers are normally used. Also, it can be used for to liquefy natural gas. The recent developments in JT cryocoolers are, instead of using a single gas, we can use mixed refrigerant. And if I use mixed refrigerant, my pressure limits are coming down. All right. So, this is a very recent phenomena, very recent developments happening in this field. And also, instead of a moving compressor, one can use a sorption compressor also. So, gas can be adsorbed, the gas can be desorbed. So, sorption compressor is a latest phenomena people are looking at, as a result of which nothing will be moving in a JT cryocooler. So, these are the different highlights of JT cryocooler. The advantages of are nothing moving on the cold side. So, no cold moving part, steady flow operation and therefore no vibration. You got a high pressure line and low pressure line, nothing oscillating, no pressures are oscillating. There is no oscillating flow in this case and therefore no vibration. The cold end can be miniaturized. So, a lot of research is going on to miniaturize this end. Can we have a micro heat exchanger for example? And this is a lot of developments are happening on this, and this is a very good advantage of a JT cryocooler. Disadvantages are one has to depend on the inversion temperature. So, real gas behavior, we can't use the ideal gas. Real gas behavior has to worry, we have to worry about its inversion temperature. It requires high pressure of the order of 200 bar if I use a single gas, and therefore, the pressure requirements are very high in this case. And because of the orifice or a capillary tubes, sometimes it can get clogged, it can get blocked with the impurities, and therefore, this is susceptible to clogging, and this is a very important thing that many times this has to be cleaned. Sometimes the blockage can happen if the water vapor comes with the gas, it can get ice formed over here and it can block the flow of the gas. This is a very important thing, and this is one of the disadvantages of a JT cryocooler. Of course, the efficiency is also low in this case. Now, if I see Stirling cryocoolers here, they are used very predominantly to cool the infrared sensors in satellites in space application. So, all the satellite experiments normally will be using Stirling type cryocoolers or Stirling coolers. It can also be used to cool the high temperature superconductors. And also, we have seen earlier that the Stirling cryocoolers, several Stirling cryocoolers working together can be used for nitrogen, air, hydrogen liquefaction. We have seen this in air liquefaction earlier. So, Stirling cryocoolers have been used for quite some time and their usages have been very, very significant. The recent developments are linear compressors, which is a dry compressor being used, which uses a flexure bearing in this case. We got a gas bearing also nowadays to smoothen the flow of the gas between the compressor and the displacer, compressor piston. So, gas bearing effect also can be realized in Stirling cryocoolers. We can do easily multi-staging to reach a lower and lower temperature, and that is where hydrogen can be liquefied. If I can go for a 2-stage unit to generate 20 Kelvin, this can be used for various end usage application. So, advantages of Stirling cryocoolers is basically high efficiency, small size and weight, it's a reliable operation, practically zero maintenance if possibly designed correctly. The disadvantages are dry or no lubrications many times, vibration due to mechanical displacer. Now, this is the moving part and therefore, you can have some vibration at this end, because of which it cannot be used in some places where vibrations are not acceptable. The GM cooler, as we know, we have just seen the GM cooler which has got a valve mechanism over here. It is widely used in cryopumps. It is a very important usage of GM cryocoolers. It is being widely used in cryopumps. It is also used on MRI machines and NMR equipments. The very important thing about GM coolers. On every MRI machine, you find GM cooler being used for shield cooling. Well, NMR also it uses for cold probe purposes. So, GM cooler is being used in various applications for cooling of superconducting magnets. Recent developments, one can go for 4 Kelvin coolers, use of rare earth regenerator materials in the regenerator for second stage, and the advantages are it can reach 4 Kelvin in 2 stages. It has got proven reliability for quite some times. It is a low frequency machine, as you know, and therefore the vibrations are at low frequency here. The disadvantages are, however, it has got a vibrations which is not acceptable sometimes at various applications. Less efficiency, as we pointed out, every GM cooler is basically of less efficiency because of the presence of valves, and of course it is a noisy. One can know that the displacer is moving up and down all the time because it uses sealing also at this point, which is also a disadvantageous in a GM cryocoolers. Yeah, here is a disadvantage. It requires sealing at low temperature, and as you know, sealing at low temperature is not a very easy task, and this sealing is rubbing basically at this point, which is also very disadvantageous. Pulse tube cooler has the biggest advantages of having no displacer and therefore no mechanical drive, and therefore no vibrations or less vibration in this case. It can also be used for cooling infrared sensors. It can be used in space application. It is just being used now, the usage has just started. Importantly, however, it can be used to recondense liquid helium and liquid nitrogen, which is very important because the vibrations in this case will be very minimum, and therefore it can, whatever helium get boiled off, it can get condensed, whatever nitrogen is boiled off, it can get condensed, and that much of cooling effect can be offered by pulse tube cryocooler. The recent development, pulse tube cryocoolers can easily reach below 4 Kelvin. It can be miniaturized. So, you can have a high frequency Stirling type machines which can be used for cooling, producing cold. The advantages are no cold moving parts, as you know here, nothing is moving. No sealing requirement because there is no displacer here. There is no sealing requirement at low temperature, which is very much required in GM coolers. Less vibration at the cold end because there is no mechanical displacer at this point. The disadvantages are there is no much reliability data right now available because pulse tube coolers have been recently used after 2000 in space application, for example. So, we do not have a time data over a period of time to show its reliability as compared to what we have with Stirling coolers. Stirling cooler has an orientation effect. It is one of the most disadvantageous thing about the Stirling type pulse tube cooler or pulse tube cooler is this being a gas phenomena, there is no displacer, it has got its inclination effect. If it is used with gravity against gravity, it does show some lessening of cooling effect with orientation, and this is the parameter, this is the design aspect which is being considered, which is under research at the moment. Having seen all these different cryocoolers, let us just see the overall applications of various cryocoolers. So, cryocoolers are used in following areas as just shown in space, military, night vision camera, the infrared cameras, infrared detector cooling in space and satellite, which is a very important aspect of cryocooling in space. The gas industry uses cryocooler for gas cooling, liquefaction, storage and cryopumps. It's a very important usage of cryocoolers. Similarly, in medicine, cryogenic catheter, cryosurgery, wherever at low temperature you want to do surgery, cryocoolers can be used. They are also used in superconductivity. So, we can have a magnetic levitation train, it will use cryocoolers, superconducting transformer, it will use cryocoolers. They are all aspects of research being carried out. They will all use cryocoolers to give cold all the time. They will use cryogens also and they may use cryocoolers also. So, trains, superconducting transformer, motors and generator will use cryocoolers for its applications. In the energy sector also at SMES, where superconducting magnet energy storage devices, you can have energy also at CERN, Large Hadron Collider usage, cryocoolers are being used in forms of cryopumps or also as cryocoolers in this sector. Of course, cooling of MRI, NMR and superconducting magnets, cryocoolers are predominantly used right now. In fact, the cryocoolers being used in MRI is one of the most important boost for the cryocooler industry because this is the most commercial application right now, which has really initiated or attracted cryocoolers to be produced in large number, and because of which the cryocooler costs have come down. Lastly, giving the summary, a cryocooler is a mechanical device which generates low temperature due to compression and expansion of gas. We need cryocoolers because it eliminates cryogen requirements and offer reliable operation. Cost of cryogen is increasing whereas the cost of cryocoolers is decreasing. Heat exchangers can either be regenerative or recuperative type depending upon the kind of heat exchange. In the recuperative heat exchanger, direct heat transfer, whereas in regenerative heat exchanger, it is indirect heat transfer. The example of recuperative cryocoolers are JT, Brighton and Cloud cryocoolers. Example of regenerative cryocoolers are Stirling, Gifford-McMahon, pulse tube cryocoolers which we just saw. The cryocoolers are used in various applications in space, gas, medicine, superconductivity applications. Finally, we have got some self-assessment exercise for you at the end, and please go through, kindly assess yourself for the lecture, and also we are given answers for this. So, please go through these questions, assess yourself honestly and see if your answers matches with the answers given at the end. Thank you very much.